I will do, I would say, general overview about energy distribution technologies. So it's not highly focused on the backup power, but I think it's a key enabler for backup power technologies. So I will welcome you to a kind of paradigm shift in the electric energy transmission and conversion. And we, from the Level company, call it Real-Time Energy Routing. So let's discover what's behind this technology and why we think it's so incredibly powerful. The question is, what if we could supply electricity from any source in any amount to any place without any conversion device? I will invite you to free your brain from the worries of energy conversion and backup power. Why our vision is so important? AI data center demands really high power, and it's exploding up to 1 megawatt to 1 rack. Building blocks are reaching the size of Manhattan, and we are facing with rapidly changing energy grids. Landscapes need more flexibility, and also we have to minimize the risk of blackouts and maximize scalability and recombinability. So the question is, what if we can solve all these problems in one new global architecture? This architecture will give us independence from server equipment, independence from power infrastructure equipments, from detailed requirements, from battery technologies, and also vendors. So we can scale up and down the grid inside the architecture as we need. So we can avoid single point of failures, create a lot of redundancies without thinking about it, because the new architecture is creating this system inherent. What's the trick? We create modular energy blocks. So we send not a stream like a voltage and amp flow, we send energy blocks from the source to the load and backwards. How to do it with a sine wave? We have to cut the sine wave into blocks, and then we are able to supply any type of energy from any source in any amount to any place without the conventional standard conversion devices like DC-DC converter or AC-DC or DC-AC converter. So the architecture is freeing up our mind, and we are reaching a new dimension without painful worries about power conversion and backup power. And we are able to adapt any new application in this global architecture. So we are making power grid safer and system inherent safer without standard conversion and transmission devices. But how it works in detail. In the standard case, we have instead this RER router busbar system. So we have multiple feeders on the incomer side and multiple feeders on the outgoing stream. And we have, in standard case, pure switches. In our case, we are dealing with energy blocks like a normal data router. So we can handle hundreds of mixed energy streams, and we ensure that the source and the sink are getting the right blocks. So a busbar is really difficult to control and to monitor because everything is analog energy flow. And now we are going to a digital energy transmission, which is a kind like going from analog mobile communication to GSM technology. Why we think this is the right thing to do, and why energy router will make the race. The trick is the architecture is based on a micro module, which is called RER, Real-Time Energy Routing Module, which is scalable in mass production. So a RER router is consisting of exactly the same modules, which are installed hundreds or thousands of times in a router. These routers are needed thousands and millions of times to connect the energy grid for one or more applications. We identified hundreds of applications in the market, for example, a data center, grid connections and interfaces between gray and white space. And we have dozens of markets. For example, energy routing is also very interesting in cars and mobile infrastructure. And all applications are reached with the same RER energy routing module. This is a small overview to understand how the energy routing is working. So we have two real-time energy routers in a green rectangle, and we have different sources, different loads on both sides. And in the middle, we can define a free backbone grid because we can convert inside the real-time router any energy type. So for example, you have an AC genset, you convert it with the first energy router to a DC backbone, and then you are converting it with a second real-time energy router to computing power like high or low voltage DC. So I think it's the same which we have done with a fiber backbone grid for data communication. So it's also media independent, and that's the trick for the power grid. Now we are able to send power in any amount to the right place. What does it mean for data center? I try to make a really short run over. At the moment, we are dealing with AC on the gray space supply and DC in the rack environment. We have different types of backup power. So the oldest version is having battery storages on the AC side, which is a lossy principle, because you have to convert AC to DC and then DC to AC, and then you're converting the AC back to DC. The next step is having the power shelves with BBU blocks and having DC on the battery and DC on the output. Then you have different mix types, and at the end we are discussing about 800 volt DC now and bringing the DC into the racks. So we have a high efficient DC-DC conversion and BBU on the high voltage side, and as necessary we have BBU on the low voltage side. So we can mix it up. What I'm focusing on is to eliminate the bus bars because they are really uncontrollable if you scale to high megawatt scale. So what is the solution? Everything is removed.
Gerald, may I ask a question?
Yeah.
Please, can we go back to the previous slide? Because this is something that I want to share from my humble background with Meta, is that usually for the servers and the GPUs and this kind of computer loads, we don't tend to supply them with the UPS power, because literally this is like a huge amount of load. So the UPS power is only dedicated for the backbone of the network. You know what I mean, like the building frame, centralized building frame. So it's only for the network. But when it comes to the power feeding the servers, feeding the GPUs, we are using just normal power, not the UPS power, because otherwise we are going to use huge power, UPS power, which is going to be really unrealistically available or commercially available. Just I'm sharing here. I don't know if there are some other places that they are feeding the GPUs or the normal servers with the UPS power. I'm not sure.
A good point. I think it's a little bit independent from the application of the whole data center. If it's a part of
You got what I mean? I mean, we are only saving the UPS power for the network.
course.
Yes, that's all. This is the most critical thing. But the data halls itself, it's non-UPS power.
Yeah. I'm trying to say, if you have a critical infrastructure data center, which is, for example, coordinating the electrical energy grid itself, then you're trying to back up the whole data center or major server infrastructure to be able to work in the case of a blackout.
In case of a blackout, my backup is emergency diesel generator.
Yes.
So, but again, they are not UPS. It's
Yeah.
a normal power.
Yeah, got it.
So I have the grid, I have the emergency diesel generator, and this is for the main bulk load of the servers in the data hall. Only the network or the core network is fed by UPS power. I hope that I'm just wanted to share this, because I'm not sure that if there are data centers out there that they are feeding the servers and the GPUs with the UPS.
Okay. I will jump in the next slide.
Sure. We can discuss this offline if you want.
And we can discuss this later. I think it's really interesting because there are a lot of combinations of backup power and I would say the use cases inside the data center. So you have different service levels. What I try to introduce is, if you are using energy routing infrastructure with everywhere the same energy routers, like using normal switches and routers, then you are able to work on the gray space, on the white space with the same RER energy routing modules. And you are able to form back-end grids, like 800-volt DC grid. And you're able to feed 48 volts to standard server infrastructure. You are able to feed bus bars, and also you are able to feed 800-volt racks or servers in the future, which have a high demand of energy. This is only an example. In practice, we have to fit it to the customer needs. So of course you have an infrastructure switch, which is also fed. It's not shown here. I think from the energy distribution point of view, we are able to build really fast, and we are really flexible on the input and output feeder, because everything is the same given from the architecture. We can integrate multi-backup power, like batteries inside the real-time energy routers or on external interfaces. So we can supply the end users, like, for example, a cooling system with a different service level and security level compared with server boards. So we are able to distribute, in a case of backup power and blackout in the outside grid, we are able to supply the core technologies with a high priority. So we do this with the system inherent storage and, of course, external energy sources like solar power and, of course, the general diesel genset. What I'm trying to show in this graph is that we can also do a retrofit to the existing infrastructure with the real-time energy routing. Here are some facts about the demonstrator setup. Of course, it's not the last version. In this setup, I show that you can build energy streams from energy blocks using batteries as energy storage element in energy routing modules. So it's only an architecture overview. And of course, we are working to integrate the data communication, the green cables, and the red cables with the power lines in one cable system. Yeah, today we are looking for people who are able to recognize what new business opportunities arising from this fundamental paradigm shift in energy architecture and tackle them together with us. So we involve everyone for good ideas how to create an open energy protocol to transmit energy in blocks. And then we call this result in this project Real-Time Energy Routing Protocol. Thank you for your attention. I keep screen sharing to be able for jumps back in the slides. Any questions?
Thank you, Gerald. I have a question. So just some background on N-Level. How long has the company been around? And the solution that you're showing, has it been deployed in data centers yet?
We have no deploy at the moment because it's, I would say, in an early stage of development compared to serious production and full tested equipment, which is delivered to data center. The company is working since 4-5 years in this topic. But my background is really deep in the energy infrastructure from my first jobs and last career point at Tesla and the Gigafactory Berlin. So I think driven from all these backgrounds and needs, I invented and created this new energy distribution infrastructure because I'm trying to eliminate all the hundreds of different conversion devices which are needed today.
Gerald, can I ask you a question? Did you have a prototype in the lab now for this?
Yes, I
So
have.
how big just I'm curious to know how big the power scale is.
The power scale today is 3.5 kilowatt. And
Oh, okay.
the rack is, it's a full rack. But
3.5 is not even enough to feed one rack
of course,
of a traditional rack in a data center, in a air-cooled data center, right?
yeah, of course, I know this. But I designed this, I would say, hardware architecture in such a, I would say, oversized dimension to have a good access for my fingers and changes for, I would say, future developments. The demonstration rack is not the end user rack, which is, I would say, adapted to the application of a data center. It's a, I would say, laboratory and development rack today.
Okay, and which battery you are deploying here?
At the moment, I'm using old car batteries because they are the easiest to handle.
Mm.
I think if the demand is very high to use lithium-ion batteries, I can do this because it's only changing the battery model and how to handle the chemistry. This is not my focus to care about battery chemistry. I'm trying to care how to cut multiple scene waves into energy blocks and how to recombine the energy blocks into data streams.
Okay, thank you.
What do you think is the biggest advantage, Gerald, from your solution? Do you have, like, even if it's on paper, do you have a design that would have higher density for this solution?
I think yes, because the losses are really low. Why the losses are so low? We do not convert the energy, we only cut them. So normally and traditionally, you try to, for example, if you have a sine wave, you try to rectify it and to smooth the DC output. But we do not need to do it. We cut the energy blocks out and we sort the energy blocks by software. And then we recombine the energy blocks in any type of stream. And then we have, for example, a DC stream to a load. So it's only energy cutting, and energy cutting is nearly lossless.
Okay, thank you. Any other questions for Gerald?
Sorry, Gerald, when you mention energy cutting, are you talking about still you are using semiconductors like transistors, IGBTs to be able to do that, or you are using some kind of different techniques?
Yes, we are using semiconductors, power semiconductors. What is really good to know is that the requirements for these semiconductors are really low. Why? The semiconductor itself has only to handle its own energy block. So for example, in my case, 24-volt DC. And everything is recombined from these small energy blocks, raising up the number of modules in the system. So one module is really, I would say, small. It's only about 300 watt or 500 watt at the moment, but in the full system, you have multiple kilowatt.
So these power modules, they are working same like the semiconductors, but in a different way. So there is no switching activities, there is no harmonics, there is no. Is that what this is the advantage of over the switching power devices?
Yeah, they are working with power semiconductors, but you have no like classical pulse width modulation, where you try to cut, for example, 800 volt into really, really small pieces in a microseconds or nanoseconds. If you compare to this diagram, I have a lot of time to do the cutting procedures for the blocks, because it's 10 milliseconds half period.
So you don't have the harmonics problem, harmonics generated by the switching devices.
No, because the small pieces are creating nearly no harmonics.
Okay, that's why efficiency is high.
Yeah, that's a side effect. It's the highest efficiency that I can imagine.
It's actually if we have high efficiency, less losses, this is a good for data centers.
I think so, yes. And I think it's really good to be able to feed the loads with different types of power. And you have at the same time the option to prioritize the distribution. Like, for example, if you have a video stream in the data net, it's a real-time application. And if you have maybe a data download, it's you can schedule it. In this case, we can do the same with electrical energy. So some users are getting a really smooth stream, and if energy is going shorted, we cut off some end user.
Okay, thank you. So can you let us how to help you, how to support you? I mean, from our previous background, our previous experience, how can we support you?
The core mission for me is to have application-related project, example for data centers, and to do with a high-skilled people a really good specification for this project. And then I can do real-time energy routing architecture fit for this project, calculate the optimal module sizes, and then we can start with rolling out the architecture. The steps are, I would say, a kind of pre-seed phase. So I need some money to investigate the project. And the next step is to find an investment for the application project itself.
Gerald, where is your company based?
In Cologne, in Germany.
In Germany. Okay. And do you have any plans to be at OCP in San Jose next month?
I planned it, but I'm trying to investigate my rare resources into further development of the technology.
Okay.
So I will attend to Barcelona in EMEA.
Okay. I'm based in Spain, by the way, so
So maybe, yes.
the chance you're coming this way, we can certainly meet. I think this is really interesting. Selfishly, you know, I think that this does seem like it would have some applications to back up power as far as this work stream. But I also know that there's a larger discussion related to power overall in the data center that I've been talking to Mark Dancy about. So maybe it fits under, you know, under that initiative. So, but definitely be interested to have a conversation with you on this. And yeah, do you see, what do you see as the biggest? I mean, you've kind of shared with us the positives of this, of what you're envisioning, but is there any downside or any issues that would be difficult to overcome?
I think the most difficult point is to get acceptance to change the energy architecture for data center energy infrastructure, because there are hundreds of suppliers which are supplying specified components like switch gears, busbar, and all this stuff. And we need to have, I would say, a big table to define the standard energy routing protocol and the, I would say, best real-time energy packet. And we have to roll out this to all suppliers. That's a really, really crucial challenge. I'm not able to do this with my company. That's why I'm reaching out to OCP now. And the big advantage is if we had we had implemented these solutions, you can replace any of the parts in the energy infrastructure with standard interfaces. So you can even ramp up a part of a data center without some missing transformers, because transformers are not necessary anymore. So it's really powerful to have everything done with the same real-time energy routing module.